Okay, welcome. I'm Dimitris Goussis, and I'm a professor here in the Mechanical Engineering Department at Khalifa University. So today, I will talk to you about the research we're doing here regarding the prediction of the coronavirus spread. This is work done with my two collaborators, Drs. Rabbani and Dr. Passagis, and the work is funded by the Khalifa University. Now, predicting the epidemic spread is not my expertise, but during the early stages of the epidemic outbreak, I start talking with my colleagues in different parts of the world. So we start collecting data, visualizing data, playing with different models, and making predictions. So during this stage, I realized that the mathematical techniques I was using in my research could be useful for the prediction of the virus. So today, I will present you a summary of the work we are doing here. I'm not going to get into much details, but I will just give you the general outline of the work we're doing here. So first, I will describe the various models that currently exist and are used widely. These are population models. These are models that divide the population of a city or a country in different groups, and they model the transition from one group to the other, like from the group of healthy people to the group of infected people, according to various physical laws. These models have parameters which can be fixed, and the way to fix these parameters is on the basis of the available data. That means the daily numbers of people that are getting infected, the people that are getting recovered, and the number of disease. Now, these models have very serious limitations, and because we have to use them anyway, there are many techniques that go around these limitations and provide some solid predictions. Now, I will present these techniques, but I will spend some time at the end of my lecture in presenting you an alternative way that we use in order to make predictions, which is not hindered by the difficulties that I mentioned. So the basic compartmental model in epidemiology is the one you see here in this picture. This is a model that was introduced more than a year ago, and the scientist who introduced it got the Nobel Prize for this work. So according to this model, the population is divided in three groups: people that are healthy but susceptible to get infected, the infected people, and the people that have recovered. Now, the basis of the model is that infected people interact with the susceptible people, and they produce more infected people. Now, as I said, this was the most simple model. This model is, as I will explain later, used also pretty much today as well. But this model was extended in many ways. This is the first extension of this model, where now the population of the diseased people has been added. So again, infected people can interact with the susceptible people to produce more infected people, which then either recover or they die. Another extension is the addition of the exposed population. This is population that they have the virus, they will eventually become infected, but the virus is not strong enough in their body to infect other people. So again, the way a healthy people can get the virus, is only through the interaction with an infected person. Another extension is the addition of the populations in quarantine. These people in that group do have the virus, okay, but cannot infect other people because they are isolated. Another extension is to separate the normally infected people from the seriously infected people. So you see that now both infected population can interact with the healthy population to produce exposed and then infected people. Of course, there are even more complex models, like this one here in the right, where now another source for infection has been added, and this is the virus that exists in the environment, either in the atmosphere, so that susceptible people can become infected, or in surfaces where healthy people can touch, and through that they can become infected. So as you see, the model becomes more and more complicated. This is another, on the left, quite complicated model. Was produced recently, 2012, and involves a large number of various infected people at different stages of the infection. Now, usually, all these boxes that you see here that represent a specific population are considered homogeneous. That means they make no distinction of the age, gender, profession, or health of the people that belong in that group. Now, an extension of this model is to divide these populations, each of these populations, in different segments. One way is to divide it according to the people's age. So, for example, in each of these populations here, you can have smaller boxes, each one containing people at a different age range. Same thing can be done with the gender, the profession, and the health status of the people in each population. Another extension for the use of these models is not to use one model for the whole country, but to use the model in the population of different major cities. Like, for example, here in the Emirates, there are 3 different models applied in 3 different regions of the country, and then combine in certain way the results. Now, a very important component of these models is the laws by which a certain person can move from one population to the other. These laws can vary from very simple to very complex. Now, all these models were used by many people during the last few months in order to make predictions on how the outbreak will evolve. In the early stages, where we knew very little about this, these works provided significant directions on making policy decisions. Now, here in this page, I present 2 of these works. The first on the left is a paper produced by Imperial College, and this specific paper was the cause for changing the policy of the government of United Kingdom and to enforce the lockdown. On the right is a similar work from German and Polish scientists that had the same effect, and formed the basis for the German government to enact the lockdown as well. Now, what's important is that the work on the left dealt with 11 European countries. So they analyzed the data that were available at that time from 11 European countries. So they cover extended geographical regions, while the work on the right dealt with the houses in Berlin, that's the capital of Germany, and another city, Wrocław, a very big city of Poland, which is across the border. So what they did there is they applied the most simple model that I presented in the very beginning to every house in these two cities, and then they combined the result and concluded that the only way out was the full lockdown. There were also other developments, scientific developments, that were produced in the early stages of the outbreak, and dealt with predicting the needs for medical care. So here you see a program, a computer code which is available, publicly available, was made by Stanford University, publicly available as soon as it was prepared, in order to predict the medical needs of a certain region. Now, although these models, as I said, were shown to be very useful, in order to produce good results, they had to go around some significant difficulties that these models exhibit. So I will talk about this next. Now, as I said, these models have some parameters, the values of which they have to be fixed. And the way these parameters are fixed is on the basis of the available data. What you see here is, on the left, is the model that is one of the models that we used. On the right, you see the available data for New Zealand. And what you see here is the numerical solution that was obtained on the basis of the model on the left, and the parameters fitted on the available data. Now you see, for example, that the infected people, that's the black line here, follows pretty much the available data. The recovered population, this is the blue line here, again qualitatively follows the available data again. Can be shown that the disease also curve follows pretty much the available data. And what you see on top of that here is this purple curve is the predicted evolution of the exposed population, for which there are no data. Now, as you can see, the solution of this model pretty much provide good qualitative results, but are not good quantitative. Now, this technique is not, in general, good for predictions. And this is what I will just show. So here I will consider the data from South Korea. So again, we use this model on the left. We took the data from South Korea, we fixed the parameters, and we got the solution. The problem was that with each data for a new day added to the data that we used to get the values for the parameters, we're getting very different solutions for the model. And this is what I will show you now. I will show you two videos in which you will see how much effect is the addition of one data point to the solution that we get from this model. Now, first, I will start with the infected people. So the circles here denote the available data, and the line is the solution that we get from this data. So you see now we add 1 point, data point, and we get a different solution. Now you can tell how drastic is the effect of adding one data point to the solution that we get out of this model. And remember, what you see here are profiles of the infected people for which we have data. What you're going to see on the right is the corresponding profiles that we get for the exposed population for which we have no data. So I repeat, these are solutions that we get from the model on the left when we add one more data set of points each time in order to fit the parameters of the model. So now you see the problem. In mathematics, this is called an ill-conditioned problem. And the idea is that, in this case, that adding one set of data in order to fit the parameters, you get a completely different solution. So clearly, these models are not accurate in order to make predictions, because as you can see, the solutions we get cover a very wide range. Now, in order to overcome this problem, mathematicians develop specific techniques which, instead of providing a single curve, they provide a range of values which are the expected values in the future. So this is on here, where here on the left, this is again from the Imperial College report I mentioned before, and here you find this applies to United Kingdom, and on the left you find the daily number of infections as a function of time, and you see that instead of a single curve, they provide a range of values. In the middle you find the number of deaths as a function of time, and on the right you find how the reproduction number evolves again with time. Now, this range of values is called credibility interval, and as you can see, they provide ranges in that interval of specific percentage for that to happen. So light color represents 50% for the solution to lie there, and light color is 95% for the solution to be there, and the dark color represents a 50% solution, 50% for the solution to lie in this region. Now, these estimates were shown to be very accurate and very helpful for making policy decisions. So, but the question still is whether it is possible to make more specific conditions. Now, and this is what is the topic of my research, and I will just provide you the outlines of this type of research. Now, this research of mine is based on the notion of the time scales. Time scale is a certain time period that characterizes the evolution of a certain process. For example, when boiling an egg, we say that this process lasts 6, 7 minutes. Okay, so we say 7 minutes, and we don't use the equivalent of an hour, which is 0.11 hours. So in our mind, the time scale for this process is the minute. Again, if we fly overseas, for example, if we fly to Athens, we say that the flight lasts 5 hours. Okay, we don't use the minutes, and we don't say that the flight lasts 300 minutes. Okay, because in our mind, the time scale for this process is hours. Now, these time scales for these two specific processes are fixed. Okay, boiling an egg is always 7 minutes. Flying to Athens is always 5 hours. But in some other processes, our perception of time scale changes. For example, as we grow up, when we are young, we measure times in years, but when we get older, we measure times in decades. So I use this example in order to convey you the idea that the time scale notion is something that we use every day, and is something that unconsciously, okay, we use it in order to take decisions. So I will give some more details on this. Again, I use this model. I repeat, this model starts with susceptible population. These are a healthy population, which is prone to get the virus. We have the exposed population. This is people that got the virus, but the virus is not strong enough yet to infect other people. Then we have infected population, two classes of infected population, normally symptomatic population and seriously symptomatic population. And then we have the diseased population and the recovered population. So we use this model on the available data from China in the early part of the outbreak, shown here with circles. Okay, black are the infected people, red the recovered people, and blue the diseased people. And with lines are the solutions that we got from this model. Now, here are the profiles for the various populations that we got on the basis of this model. Now, we just saw before that although qualitatively the results in the region where we fitted the data is good, the results far away from this region are not good and are not to be trusted. So we look at this solution and we computed the timescales. Now, I'm not going to go into the details here, but I just want to point out that with red are shown what we call explosive timescales. These are timescales that characterizes processes that lead away for equilibrium. So these are the processes that make things happen, while with black are timescales that characterize processes that lead to equilibrium. Of course, these processes make things happen, but these are the things that lead the system to equilibrium. And when we look at the outbreak of a phenomenon, we should only look at the explosive timescales. And this is what is shown here. These are the two timescales we see, the two explosive timescales that we see on the left, but enlarged. And as you can see here, there is a fast timescale here, and there's a slow timescale here. They get together and then they disappear. Now, of these two timescales, the one which is more important always is the fastest one, and this is the one which is down here. And if we look at the origin of this timescale, we see that early on, this timescale is generated by the red paths here, these are the paths that lead to infection, while the black paths, these are the paths that lead to recovery, have very little effect, while later on, in the neighborhood where the two time scales are about to disappear, the recovery paths are stronger than the infecting paths. And this is the reason why this time scale disappears. Now, the end of this explosive time scale is very important, because as you can see here, this is the end of the explosive time scale. This is superimposed here on the profiles. The end of the explosive period indicates the inflection point of the susceptible and exposed profiles. Inflection point is the point where I can say it's simple. Inflection point is a point which indicates that the maximum is nearby. So this point does not indicate the maximum of, say, the exposed population, okay, but it indicates that the maximum of the exposed population is very close, as it is shown also in this case. Now, we will test this and see whether this estimate is first accurate and second, it is robust. Accurate means whether this mathematical finding is validated by the available data, and the second, robust, means whether it is valid when we use different data, when we use a different way to fit the model, or if we use a different model altogether. So here you see what we got for different countries. This is the explosive states. These numbers are in days. And here is the inflection point of the exposed and susceptible population. Now you see that in all these cases, these predictions are very close to the end of the explosive time scale, which shows that relying on the estimate, on the prediction of the explosive time scale provides an accurate number for making decisions. But what about when you look at the real data? Okay, so here are the data for Italy. This is what you see with black dots are the number of infected population. And we apply these two models on the same data set. From the model on the left, we expect to get an estimate on the inflection point of the exposed population, and with the model on the right, we expect to get an estimate on the infected population. Now here with red is the prediction for the exposed population according to this model, and with purple is the prediction of the infected population on the basis of this very simple model. Now, of course, the exposed population, we don't have actual data to compare, but you can tell, those of you that know what mathematically means inflection point, you can see that the inflection point of the infected people is in a very good position. So, and this is a good demonstration that our theoretical finding is validated by the actual data. Now, the question now is whether this prediction applies to different countries. So what we have here are data, are basically the explosive time scales computed on the basis of data from 3 countries, China, Italy, and Spain. And we computed the explosive time scale by using a small set of data, which is indicated here by the red arrow here in all 3 cases, and with a much bigger set of data, which is indicated by the black arrows here. In all 3 cases, this region extends much to the right of the period shown in these graphs. And as you can see, the point in time where the explosive regime ends is pretty much robust. Not only that, but the explosive time scale for the greatest part of the explosive region in all 3 countries is pretty close. It's 3.6 days for China, 4.1 for Italy, 4.7 for Spain, which, and this is the case also for other countries we examine, which this must be something which characterizes this particular pandemic. Now, the other test we did in order to determine the robustness of our technique was to use different models. So what you see here are the explosive time scales computed from data from Italy on the basis of the very simple model here on the left, and on the basis of this more complex model on the right. And again, you see that the fast time scale, which is of interest, is almost identical, and the explosive period is pretty much the same. Now, all these tests and other tests that we have done indicate that this technique is a very robust technique in making predictions and does not depend on the model we use, on the number of data sets we use, or even the fitting method that we use. That is the technique that we get the parameters, the values for the parameters of the model out of the available data sets. We look at different features of the evolution of the pandemic. One of them was the resurgence. That is when the pandemic seems to die out, but then for some reason, probably because of changing policies, probably because of changing the habits of the population, then the outbreak starts up again. So we examine the case of Pakistan. You see here on the left, you see the number of infected population and the number of diseased population. And you see that up to some point, things were getting under control. But at some point, the lockdown was relaxed. And as you can see here, both infected and diseased people increased very much with time. So we looked at these 2 different periods, and we examined the explosive time scales and also the explosive period. And the results are here on the right. Now, what you see here is that the first stage, the explosive time scale is much faster than in the second stage, which means, contrary to what we see here, the process to be faster early on than later on. And there are some reasons for that. I don't have to explain, but we did try to figure out the origin of this problem. And we look at the processes that contributed to this phenomenon. That is, I repeat, the issue that we're looking at was why, in the first stage of the spread, the spreading time scale was faster than in the period that followed. And what we found is that the infecting paths were, of course, playing a significant role early on in both stages, a diminished role at the end of these two stages, but the big difference was on the recovery paths. They play a much stronger role in the second stage of the spread than in the first, and this is the reason why this explosive regime was much shorter than the one at the start. And this is again a finding that, of course, one can think of, okay, but now this is quantified by this mathematical theory. So with this, I would like to conclude and say that we are now confident that our technique provides robust results, much more robust and more precise results than the currently available prediction techniques. We're still working on this. We emphasize more on the resurgence, which is something that concerns all countries around the world. And we look at also at how different factors influence the spread. We try to find similarities and differences among different countries. And also we try to assess the usefulness of the various models that are currently in use. So with this, I would like to conclude. I would like to thank you for being here, and I'm waiting for your questions. Thank you. Okay, so I will read some questions you sent me. By reducing the deaths and the recovered people, the infected people should be isolated, right? This is true, and this is the reason why they add this population in one of the models I showed you before, which represents the people in isolation. How can we make sure that we don't get the virus if no one is isolated and everyone is meeting? Of course, yeah, we cannot guarantee that, and this is why we take all these measures. How long do you think that the virus will last? That I don't know. I don't know. Okay, so there are no more questions. I would like to thank you once more. Bye.